Hello, I'm Anna Mackay and this video is on stationary points. So a refresher as to what they are. They are when the derivative is equal to 0, and that means the tangent at that point would be horizontal, so that the rate of change or the slope of that tangent would be 0 and therefore horizontal. Thinking about on this graph here where those stationary points, stationary meaning stopped, so the function here has a maximum at this point. Continuing on, we would have a minimum, sometimes called a local minimum, at the bottom here. And then this one over here is a stationary point, but it also doubles up as an inflection point. We'll get into more detail about those in the next video. Right, some examples. If we're asked to find the exact position and nature of stationary points of this function here. So our first step, when in doubt, differentiate. So to find out the derivative, we have negative 12x cubed plus 12x squared. And we need to factorize that, well, because we need to say that f dash of x is equal to 0, stationary points. So then set that equal to 0. You could start factorizing straight away if you like. Taking out a factor of 12 and x squared. Always take out a leading negative if there is one there to leave us with bracket x take 1. And solving for x using null factor laws, it would be when x is equal to 0, which comes from that factor there, and 1. Now don't stop there. Go back and read the question. Find the exact position and nature. So we need to draw a sign diagram for this. So we have our sign diagram, and this is the sign diagram of the derivative, f dash of x. You put on your two values, your critical values, 0 and 1. And now you might ask yourself, right, I've got to put signs on this, but what does it look like? So, as you should do with every question, is create a visual for yourself. So grab out your graphics calculator if you haven't done it already and put that in, graph it, see what it looks like, so you know what you're heading towards. We should have probably done that at the beginning. I'm going to draw a very quick average sketch here, and it should look something a bit like this. So having a think about how many stationary points this is going to have, we have one here and one here. Now when it comes to putting the signs on this sign diagram, two ways of doing that. You could substitute numbers in. Let's substitute one in over here. Let's substitute in the number 2. Where do you substitute it into though? You want to get a positive or a negative value. If you substituted it into the function, you're actually working out, if we substituted in 2, you would be working out the y value when x is 2. We don't want that. We want to know what the slope would be like, so we substitute that into the function. If you substitute 2 into here, what are you going to get? Either one is fine to substitute it into. You would get a negative number. So on our sign diagram, that would be a negative. Now that matches with our picture, because from this point onwards, from 1, it's decreasing. If you were walking along this line, from this point here on, you'd be going downhill, and that matches with our negative sign. So in terms of what other signs to put here, we are increasing and have a pause, a stationary point, and then continue to increase, and increases correlate with positive signs. But don't stop there. We have to define their nature and their position. So their position is found by substituting these numbers now back into the function. So f of 0 and f of 1. So we have f of 0 gives us, everything else cancels out, 2. Good habit to get in to write that as a coordinate. And the other one at 1 gives us, well, negative 3 plus 4 plus 2 is equal to 3. So 1, 3, these are our 2 points, so that's their position and the nature. Here we have that, this is the easiest one to identify, it's a local maximum. So we say local max. And this one is a stationary point, but also a point of inflection. So it's called a stationary inflection. Stationary with ARY, not ERY. I think of it like car has an A in it, and cars stop, if that makes sense. Okay, so that's how to complete that question. Next one, find the exact position and nature of stationary points of this function. So it's an exponential. Draw it on your calculator. See what it's going to look like first of all. I will give you a hint, but don't rely on me. What if I'm wrong? It might look something approximately like this. So how many stationary points are you expecting? 1 would be your answer, so that you know what you're heading towards. How do we find them out? We need to differentiate. Feel free to use either terminology, the function notation or the dy by dx. I prefer the function notation. So looking at this, we're going to need product rule. So we differentiate e first, so you copy and paste and you differentiate the power and you put next to it the second function. And then you add on where you leave the first and you differentiate the second, which gives us this. Tidy it up to get negative e to the power of negative x, 2x plus 1 plus 2, e to the negative x. Now, stationary points happen when the derivative is equal to 0. So that means we have to factorize this. So start having a look at what could be common. And hopefully you'd agree that there's an e to the power of negative x is common. To take out a leading negative or not here is debatable. So I'm not going to this time around. And what is left over? Now careful with the negatives here because that negative needs to take into account for this 2x and the negative 1. And what's left over in this term, we have positive 2. Simplifying that to get negative 2x plus 1. So it's when that is equal to 0. Perhaps I should have put equals 0 there and not worried about those equals. Now, e to the x functions or e to the negative x functions are always greater than 0. And feel free to graph that and have a look. And so that's how you take that into account. So there's no stationary point that we're going to gain from that part of it. But this part here, you would have when this factor is equal to 0. And what is the x for that? Positive 1/2. So that's when this local max is going to occur. But you can't just rely on your graphics calculator to tell you that. You have to justify it. And by doing that, you must do a sign diagram and put the signs in. The signs you can read off your calculator though. So this function is increasing up to 1/2, and the symbol for increasing is positive, and then it's decreasing, so the slope of the function. And they are the symbols to indicate a maximum. So we have a local max at, now the x coordinate is 1/2. How do we work out the y? We have to take that 1/2 and substitute it into the function up here. Now, because it wants exact value, we can't just read that off our calculator. I probably haven't left myself enough room now, but I'm going to do this here. So we substitute in 1/2, and it's probably going to write over my picture here. Where you see an x, you're subbing in 1/2. This comes out to be, so e to the power of negative 1/2 will be 1 on the square root of e, and this factor over here works out to be 1 plus 1 is 2, so we have 2 on root e. That is our y coordinate for the local maximum, and that's what it means by exact position. You can't have a decimal approximation. Okay, and this one, and then just a point to add. Trig. Determine the exact position and nature of stationary points of y equals sine 2x. Graph it on your calculator and see what it looks like. And note the domain here. So you might as well restrict that, and it would look something like this. How many periods has it got? Something like that. So how many stationary points are you expecting there? How many horizontal tangents could you draw? I hope your answer is 4. Differentiating that. So we have dy by dx for a sine function. Sine, the derivative of that is cos of 2x, and then you differentiate the function. So you put that 2 there. Now, stationary points when dy by dx is equal to 0. So you put this equal to 0 and solve for x. Now you have to ask yourself, well, when is cos of 2x equal to 0? First of all, you need to start thinking about, well, when is cos of theta, so anything, equal to 0? Do a little sketch of your unit circle. cos, that's the x coordinate, when is that equal to 0? Well, that's equal to 0 at the y-intercepts. What are those in terms of pi? We've got pi on 2, 90 degrees, and 3 pi on 2. So we substitute that back in. This is going to help us solve this now. Now, in this case though, our theta is actually 2x. So usually our domain that the question has asked us is between 0 and 2 pi. But we actually want double that. So our domain that we have to take into account is double x, so 2x, so that makes it 4 pi. That's what we need to define r's for. Now, the 2x, the values for that when that is equal to 0, because we're going to divide through by 2 afterwards. So that comes from these ones over here, pi and 3 pi on 2, that we're going to write. So we've got pi on 2 and 3 pi on 2. But we need to take it into account for 4 pi. So we need to go all the way around again and say what 2 more of those would be. So we've got 5 pi on 2 and 7 pi on 2. But this is currently for 2x. We want that for just x. So that means you divide each of those terms by 2 to get pi on 4, 3 pi on 4, 5 pi on 4, and 7 pi on 4. And because we took into account this double factor in the beginning, we've already made sure that we've now got enough in our 2 pi range, if you were to sit there and work that out. Now we're not finished. We have to determine the position of each of them, that means a coordinate, and their nature. So thinking about which ones are maximums and which ones are minimums, the first and the third are maximums, and the second and the fourth are minimums. So we're going to write that neatly now. We've got local max at, now the first one was pi on 4, and the second one was 5 pi on 4. Now, how do you work out their y coordinate? You substitute in pi on 4 into sine of 2x, and you get 1 here and 1. Well, we should know that from the graph as well. And local min at 3 pi on 4 and -1, and 7 pi on 4 and -1 again. So that's that trig one. And just a note here, when you get to solve some of these more complex ones, when is cos of x equal to negative sine x, if ever you need something like that? Think about your unit circle. Cos and sine. So we want one being positive and one being negative. The only time that could happen is with the one on the root 2 family, whereas the other one, one is a half, and then the opposite coordinate for the sine or cos will be different. But in the pi on 4 family, they will be the same. So pi on 4 is the 45 degrees. So having a think, if we have our unit circle, where 45 degrees is in each quadrant, it's there. Now think back to cast, or some silly thing about turtles, if you know that one, where things are positive and negative. So like that. So you think about this point here, cos will be positive 1 on root 2, and so will sine, because they're all positive in this quadrant. So that means for this angle, they are equal. One is not the negative of the other one. So this quadrant's out. The other quadrant that's out is this quadrant here, because they will both be negative, and that's not right. But in these quadrants, quadrant 2 and 4, we would have a negative cos value here and a positive sine, because we're up the vertical axis. So this quadrant works, and down here we would have a negative sine for the equivalent positive cos value. So when you come to solve tricky, different things like that, you need to try and visualize when that could possibly happen. Okay, make sure you subscribe and like it, and the next video in this series is called Inflections and Shape. Thank you.